Let's take a look at logarithmic functions. And the first thing we'll take a look at, as soon as I get my pen working there it goes, is we'll look at the log form. That's where you have log, and then b here, and then q, and then p. Now, this right here is called our base. It's usually a number that's smaller and kind of set down. Now we also have our exponential form, which says b to the p is equal to q. Now these first problems want us to write it in the other form. So on number 1 here, they give us 5 is equal to log base 3 of x. And instructions say write each equation in its equivalent exponential form. Well, they give it to us in log form. Again, the number that's smaller, that's kind of set down right here, that's our b. And then what follows that is our q. So this is q. And then our other side of the equals is our p. Now our exponential form is b to the p is equal to q. So we'll plug in the letters we just identified. B we said was 3, p is 5, and q is x. And that'd be your answer. Let's look at this problem. We got 5 to the third is equal to 125. Now it's given it to us in exponential form and wants us to write it in log form. Write each equation as the equivalent log form. Well, our power, our exponent, is the p, so that's p. And what's to immediate to the left of it is b. And the other side of the equals is your q. Now your log form looks like this. Log, like that. So we're going to plug in the b, which is 5. So we got log base 5, q, which is 125. So of 125 equals p, which was 3. And that'd be our answer. Let's look at our third problem. You'll see these a lot when working with logs. If you have radicals of some sort, you immediately want to write it into fractional power form, rational exponent form. Well, this we can rewrite as 16 to the 1/4 power equals 2. Whatever number's in this little slot right here, that's called your index. In this case, it's 4, and that goes down your denominator. Now, whatever power is inside here, the 16 goes up on top. There is no power here, so there's always invisible 1, so that's why we put a 1 there. Well, this is an exponent form now. So our power, our exponent, is going to be our p. What's to the left of it is going to be our b. And the other side is going to be our q. So our log form looks like this. So let's plug in what we identified. B we said was 16. Q we said was 2. And P was 1/4. So that'd be our answer. Log base 16 of 2 is equal to 1/4. Now in this next problem, I'm going to go ahead and solve it, and then I'm going to write the formula down. Formula will make it look a little kind of complex, but it's a very simple idea. It says, evaluate each expression without using a calculator. Well, on this particular problem, our base is 5, so we're going to try to rewrite the 25 as 5 to a power. And we can rewrite 25 as 5 squared. Well, if you can, this is our base, the 5. If you can get it to match the number that's following it there, see how the 5s match? Then the log and the 5 is going to cancel and leave us just the exponent, which is 2. Now our formula for that looks like this. We have log, and then that's b for our base. Then b to the p power is equal to p. So again, if these match, then they cancel away and leave you just the exponent. Let me work another problem. Base 2 of 1/8. Same instructions. Want to evaluate it without using a calculator. Now 8 is pretty easy. That's 2 to the third. So I'll start there. So this becomes 1 over 2 to the third. Now our formula doesn't say anything about the 2 to the power being trapped in the denominator. So I'm going to take this 2 to the third and I'll move it up on top. From intermediate algebra, algebra 2, you had a property that said we can take something opposite of where it's at in a fraction, top to the bottom, bottom to the top, and the sign of the exponent changes. So this becomes 2 to the negative 3. So again, I took the 2 to the positive 3 up on top and it became 2 to the negative 3. Well, the 2's matched now, so log and 2 is going to cancel, and we're left with the exponent, which is negative 3. Take a look at another one of those. Log base 4 of the square root of 4. Again, what we want to do is our base is 4, so we want to rewrite that as 4 to a power. And the square root is the 1/2 power. Wherever number is in this little slot right here, that's called your index, goes in your denominator. If there is no number, you put 2 there by default. And then the power that's inside, which in this case would be the 1, goes up on top. Now since the 4's match, the log and the 4's cancel, and we got 1/2. Now, let me talk about what I've done already. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I've made 17 mistakes so far on this page. I'm going to make more, and I'm happy with them. But I do want to mention them if you are going on in math. Log is never written all uppercase. It's always written lowercase. Some people get very picky about math, and I want to mention that. So if you go on, you need to realize they're supposed to be lowercase. Now I used to write them lowercase. 12 years I wrote them lowercase. I went into college algebra. I'd cover this. I'd say log this, log, log, log. You know, I'd say log 500 times during class. I'd always have somebody come up at the end of class and they'd ask me, what's this 10G you keep writing up on the board? So I knew someday my mind would snap when I got that question. It's like, you didn't make a connection between the 500 times I said log and the same time I was writing down 10G. So I make them uppercase now. I no longer get that question in seriously. Sometimes students will say it in jest, but yeah, it's supposed to be uppercase, or lowercase, I mean, sorry. So I know I'm writing it incorrectly, and I'm happy with that. Okay, so we got log. What's that, 10G? I think that 10G means I'm going to see you again next semester. It's like, how can you? That still boggles my mind. Okay, in this problem, our base is 9, and so we want to rewrite the 3 as 9 to a power. Well, if you think of what kind of connection there is between 9 and 3, well, the square root of 9 gives you 3, and square root of 9 is 9 to the 1/2. So this right here, I can rewrite the 3 as 9 to the 1/2. And now that I've done that, those 9's match, so the log of the 9 is going to cancel, and we're left with 1/2. Let's look at this one. Log base 8 of 1. Well, our base is 8, so we're going to try to rewrite 1 as 8 to a power. And anything to the 0 power is always equal to 1. So 8 to the 0 power is equal to 1. So now the 8's match, so the log and the 8's cancel, and 0 is our answer. Now, next one I'm going to go ahead and work, and then I'll write the formula down. Again, the formula makes it complex, but it's very simple. And let me open my window a little bit, get some air. There. Okay. We got 3 to the power of log base 3 of 17. Now you notice that these 3's match, don't they? So the 3's match, the log and the 3's are going to cancel, and our answer is 17. Okay, let's look at our formula for that. So b to the log base b of q is going to equal to q. So that'd be our formula for that. It's a very simple idea. Again, these match, the log and the 3's cancel, and we're just left with 17. Okay, let's look at this problem here. They want us to decide which function over here matches the graph. Let's look at the first one. F of x is equal to log base 9 of x. Now we got thought I brought up my calculator. I guess I didn't. Let me bring up the calculator, then I'll continue. Gives me time to grab a drink here too. We got 2 buttons. We got a log button here, and we got an ln button. Now this log button you see here is base 10, and this ln is base e. We're going to talk more about that later. You don't need to worry about that for now. We don't have a base 9 button. So what we have to do is we're going to use a change of base formula to rewrite it. Now what the change of base says is we can rewrite it as log of something over log of something. Now the x is going to go up on top and the 9 will go down below. The way it always works is whatever follows the log here goes on top, and whatever your base is goes down below. Now the benefits of rewriting it in that form, even though it looks more complex, is we can actually plug that in our calculator now. Because we have a log button, so let's go and plug that in and see what we get. So I'm going to press y. Let me clear all that out. Okay. So I'm going to press y equals. I'll press clear. And I'll do log. And put my x in. Closing parentheses divided by log and then 9. And closing parentheses. And then graph. Now a calculator is going to lie to us about what it looks like. It looks like it just stops. Looks like it just stops there. It doesn't. It keeps going down forever. It just got so close to the y-axis it appears 1 with it. Actually, it's a little flaw with the calculator also. It doesn't actually continue forever. It should, but it doesn't. So that's what our graph should look like. Well, if I come over here, this looks like that looks like it's been flipped across the. This is our basic graph. This looks like it's been flipped across the y-axis, reflected across the y-axis. Now remember, if your negative is out in front, it flips or reflects across the x-axis. If your negative is inside with the x, then it flips across the y-axis. So the only ones that are a possibility are h of x, because there's a negative there, I of x, which is a negative there, and k of x, because there's a negative there. Now k of x has a negative out in front. That means it would flip across the x-axis too. Well, this doesn't look like it's flipped across the x-axis if you compare that against this basic graph. It actually looks like h of x. Remember, a negative inside with the x flips it across the y-axis. So our answer, number 10, is h of x. Now I of x has a little bit of a twist to it that I want to mention. I of x is equal to log base 9 of negative x minus 1. Now if you got a number inside with the x along with a negative out in front of the x, what you have to do first is you have to factor a negative out. And that gives us x plus 1. This negative that's right here flips or reflects across the y-axis. And if you got a number inside of the x, it shifts left or right opposite what you think. The plus 1 would make me think goes right 1, so it actually goes left 1. Here we got a minus 1, that's going right 1. Here's a negative out in front, that flips across the x-axis, reflects across the x-axis. So on these particular problems, they just want you to use those facts to help figure out which one's your answer. So to remember what these negatives do, what numbers do, and so forth. Let's take a look at number 11. We got f of x is equal to log base 4 of x minus 3. It says describe the transformation and graph the function. Well, if you got a number inside with the x, it's left or right, opposite what you think. The negative 3 would make me think it goes left 3, so it really goes right 3. Now to graph this, it's got a base of 4, and we want to rewrite it. Now, instead of just writing it as log, the change of base says you can actually rewrite it in terms of any base. Now, this is base 10. This is base e. E is 2.7. So I could rewrite this as natural log of x minus 3 over natural log of 4. You could also do log of x minus 3 over log of 4. Doesn't matter which one you pick. Now, those are the only two that actually make sense because those are the only two buttons we have on our calculator, if you're going to use calculator to graph it. So let's graph this one. Now press y equals, press clear. We got natural log of the ln of x minus 3, closing parentheses, divided by natural log of 4, closing parentheses, and then graph. Well, it does look like it's been shifted right 3. And our graph looks something like that. And it doesn't just stop. It keeps going down forever like that. It just became so vertical that the calculator gets confused and drops off part of the graph. Let's look at this next one. Got f of x is equal to log x plus 3. Now, if they wanted the plus 3 to be included in with the log, then they would have put parentheses around it. So as it is, this is separate from the plus 3. Well, the plus 3 means we go up 3. And we don't have to use a change of base here because this is just a log, which is base 10. So let's go graph it. I'll press y equals, clear. I got log x, and I want to put a closing parentheses, and then plus 3 in graph. And that's somewhat our answer. It's not our actual answer, because we know they never just stop. So it goes down like this, and then keeps going forever down like that. And that's our answer. 13. Got f of x is equal to natural log of 1/3 x. Now again, we don't need to use the change of base because we got an ln button right here. So we can just plug it in directly. So I'll do y equals, clear, ln, and it's 1/3 x. So do 1 divided by 3 x, and then closing parentheses, and then graph. And not very good at sketching these, but again, it goes down forever like that. More or less looks like that. Let's take a look at the domain. Number 14. We've got f of x is equal to log base 3, I think it was. Yeah, of x minus 5. And the instructions say find the domain of each log function. So finding log. Let's try that again. Finding the domain of log function. Older I get, the more I talk and write like Yoda off of Star Wars. Sad. Finding domain of a log function. Now we can't. The idea behind this is we can't have log of 0, can't have log of a negative number. So what we're going to do is set what follows the log greater than 0 and solve. So take what follows the log and set what follows the log greater than 0 and solve. So we're going to set what follows the log, which is x minus 5, greater than 0. Now to solve this, we take the negative 5 over, and we get x is greater than 5. And that's our domain. If you want to write an interval notation, it'd look like this: 5 to infinity with parentheses around both of them. I don't care how you write it in my particular class. Let's take a look at another one. This is an oddball case. So we've got f of x is equal to natural log of x plus 3 squared. Now it's not an oddball case because of the natural log, the ln. That's just another log with a different base. It's written differently. Don't ask me why. If I'd paid better attention to my history and math some 20 years ago, I probably could tell you. But it has all the same properties, all the same rules, everything that the other logs do. So we're going to set what follows log greater than 0 and solve it. So we've got x plus 3 squared is greater than 0. Now think what happens when you square something. Like negative 2. You square a negative 2, gives you a positive 4. So you square a 2, and it gives you a positive 4. So no matter what, when you square something, it becomes positive. So this is asking, when is this greater than 0? Well, when you square it, it's always positive, which is always greater than 0. With one exception. Think of a value that I could plug in for x that would not be greater than 0. Well, that'd be negative 3. If I put negative 3 in here, negative 3 plus 3 is 0. 0 squared is 0. 0 is not greater than 0. So our domain is x cannot equal to negative 3. If you want to write an interval notation, that'd look like negative infinity to negative 3 union negative 3 to positive infinity. Now you could also use polynomial inequalities to do this. Don't know why I just did that, but let me. Remember where you get the critical value? Negative 3, and that splits it into intervals. Then you graph it. Come up with that. And x is greater than 0 means above the x-axis. It's not equal to, so it doesn't include this point. So even if you use polynomial inequalities, it's one of the oddball cases. So you could do it either way, though. Let's turn a new page. I'm going to write down what we've indicated in a few times in this section. First, if you have log of something, you don't have a base. You don't have a small number down here. Then your base is going to be 10. And this has to specifically say log. And this is a common log. Now if you have natural log, ln, then your base is going to be e. And this is a natural log. Let's look at a problem dealing with these. We got log of 10,000. Well, this is just log. There is no number here, so by default it's base 10. Now I look at how to rewrite 10,000 as 10 to a power, and there's 4 zeros, so this has to be 10 to the 4th. Well, the 10's now matched, so the log and the 10's going to cancel, and our answer is 4. So these are like some of the very first problems we looked at. On this one, We have natural log of 1 over e to the third. Well, if I were to put a base on this, natural log over here tells us base is equal to e. So I'll put an e there. Now, we looked at this earlier. If you got something to a power in your fraction, you can take it opposite of where it's at in the fraction, and the sign of the exponent changes. So I'll take the e to the third up on top, and it becomes e to the negative 3. So now these e's match, the ln and the e's cancel, and our answer is negative 3. Number 18. E to the natural log of 9x. If I were to think what base is here, natural log is base e. So I put an e here. Now these both have e's, so the natural log and the e's cancel, and our answer is 9x. And our last problem here, we got 10 log of 5x minus 2. Now we just have log here. This is our first case where we have no number, but it says log, that's base 10. Well, again, these 10s match, then log and the 10s cancel, and our answer is 5x minus 2. Now technically, you'd want to put some kind of restriction on those so that you don't have log of 0 or log of a negative number. But that's not what they're asking for here. They just want you to simplify it, find out the value of it, not worry about the domain. And I believe that's the end of that section. Yes, it is. So, logarithmic functions.